In this lesson, we explore how to write data to a file and read data from a file. When accessing files in LabVIEW, there is a typical File I/O programming flow. First, you will open or create or replace the file. Second, you will read or write to the file. Third, you will close the file when finished. And finally, you will check if an error has occurred. High-level File I/O VIs combine three steps: open, read or write, and close, all in one node. For example, executing the Write Delimited spreadsheet VI will open a file, write data to the file, and close the file. In this example, the DACMX read VI acquires multiple samples from 4 channels and outputs the data as a 2D DBL array. The Write Delimited spreadsheet VI opens or creates the file specified by the datalog file path control and then writes a header containing each channel name. The Write Delimited spreadsheet VI inserts a tab delimiter between each column item and inserts a new line character at the end of each row. The Write Delimited spreadsheet VI closes the file. Next, the Write Delimited spreadsheet VI opens the same file and then writes the 2D DBL array data to the file. Notice that the append to file terminal is set to true, which means that this VI will not overwrite the headers written by the previous Write Delimited spreadsheet VI. Notice that the VI had to first transpose the 2D array to make each column represent a channel. Again, the Write Delimited spreadsheet VI inserts a tab delimiter between each column element and a new line character at the end of each row. Lastly, the VI closes the file. Use low-level File I/O functions when you need to control each step. Low-level File I/O functions provide individual nodes for each step. In this example VI, the first function opens an ASCII text file. Then another function writes to that file repeatedly in a loop. Then the last function closes the file. As you can see, the write-to-text file function might be called hundreds of times, but the open file and close file functions only happen once. If you need to write or read multiple times to the same file, you should use low-level functions for better performance. In contrast, if you use high-level VIs inside a loop, it will open, modify, and close the file every time the loop executes, which will result in worse performance. Reference numbers are temporary pointers to a resource, such as a file, device, or object. References serve as unique identifiers of that object. A reference is created when the user opens or creates a file. In this example, the reference is wired to each File I/O function. The reference identifies which file the write-to-text file function and the close file function should access. Use low-level File I/O functions when you need to control each step. Low-level. If you want to stream or continuously write numeric data to a file, you should use the low-level File I/O functions. A common example of this is streaming your acquired data to a file. When writing numeric data to a text file, you must first convert the numeric data type to a string data type, because the write-to-text file function's input is a string data type. Let's look at how to. One way to convert numeric data to a string is by using the numeric conversion functions. This example converts the floating point numeric by using the number to fractional string function. The precision input specifies the number of digits after the decimal point in the output string. In this case, 3 digits after the decimal point. You can see that the floating point data type has been converted to a string of 0.897. Let's look at how to convert a DBL data type into a string data type using the number to fractional string function. Notice as I change the precision input value, I can adjust how many digits after the decimal point appear in the resulting string. What if you have several items and data types to convert to a single resulting string? For example, a string that looks like this. You can use a single format into string function to perform this conversion. The format into string function requires some practice to use, but it is very useful for conversions into strings. First, let's place a format into string function on the block diagram. In this example, I have 3 items that I want to convert into a string: username, sample rate, and number of samples. I'll resize the format into string function to show 3 inputs. Notice that by default, these inputs are a DBL data type. Next, I'll define the expected data types for these inputs by creating a constant for the format string input. I can then place format specifiers, or % codes, to define the data types for each input and how I want the resulting string to appear. First, I'll type in %s for a string input, then %f for a floating point input that will appear with a fractional format in the resulting string, then %d for a signed decimal integer. For more information about these and other % codes, look at the help for this function. Now I'll wire my inputs. And now I will create my resulting string indicator. Let's run the VI. As you can see, the %s has been replaced by the string input. The %f has been replaced by the DBL input and shows the DBL in a fractional format with a decimal point. And the %d has been replaced by the signed integer input. I can also type constant strings around my format specifiers in my format string input. Now when I run the VI, the resulting string looks like this. There is additional syntax available for my format specifiers. For example, I can add a 0.3 to my %f to specify the precision or number of digits after the decimal point for my floating point conversion into string. This example shows how to stream one channel, one sample data in a loop. First, we create a file. Then, we write a header to the file by writing a descriptive name for the data and an end-of-line character. Then, in the loop, we acquire one sample each iteration, use the format into string function to convert the numeric into a string, and add an end-of-line character. Then we write the resulting string to a text file. This happens in every loop iteration until the user clicks the stop button. Lastly, we exit the loop and close the file. This example shows how to stream n channels one sample data in a loop. First, we create a file using the open, create, replace file function. Then we write the column headers to the file. The string array constant contains the column headers. The array to spreadsheet string function converts the array into a single string that contains each string in the array, separated by a tab, and adds an end-of-line character at the end. Then we write this string to a file to create the header using the first write-to-text file function. Then in every loop iteration, we acquire a 1D array containing one sample from each channel, and use the array to spreadsheet string function to convert the numeric array into a single string that contains each numeric separated by a tab with an end-of-line character at the end of the string. Then we write this to the text file. This happens in every loop iteration until the user clicks the stop button. Lastly, we exit the loop and close the file. This example shows how to stream n channels, n samples of data in a loop. First, we create a file using the open, create, replace file function. Then, we write the column headers to the file. The string array constant contains the column headers. The array to spreadsheet string function converts the array into a single string that contains each string in the array, separated by a tab, and adds an end-of-line character at the end. Then we write the string to a file to create the header using the first write-to-text file function. Next, in every loop iteration, we acquire a 2D array containing multiple samples from each channel and use the transpose 2D array function so that each channel's data is represented by a column instead of a row. Then we use the array to spreadsheet string function to convert the 2D numeric array into a single string that contains each column item separated by a tab character and each row separated by an end-of-line character. Then we write this string to the text file. This happens in every loop iteration until the user clicks the stop button. Lastly, we exit the loop and close the file. The first method of creating a file or folder path is to specify a hard-coded absolute file path as shown in this file path constant in the figure. An absolute file path describes the location of a file or folder starting from the top level of the file system, such as the C drive. Another way to create a file path is to use the File Dialog Express VI to launch a file dialog box asking the user to choose a file for themselves. You can also create a relative path. A relative path describes the location of a file or folder relative to another location in the file system. The Application Directory VI returns the path to the directory containing the LabVIEW project file. In this example, the first figure uses this function and the build path function to create a relative path to the mydata.txt file in the same folder as the project file. The Get System Directory VI returns the system directory specified by its type input. The example in the second figure uses this VI and the build path function to create a path to the mydata.txt file in the user's desktop directory on their computer. For a list of available system directories, refer to the LabVIEW help. Using relative paths makes your code more portable from computer to computer. This common real-world example programmatically creates a file name based on the current date and time. The format date and time string function uses the current time as the default timestamp. The format date and time string function then converts the timestamp into a string based on its time format string input. In this example, the function converts the timestamp into a string starting with the year, then month, day, an underscore character, hour, minute, second, another underscore character, and then mydata.txt. This example uses the Application Directory VI and build path function to make this into a relative file path in the same directory as the project file. Let's say you have already collected and stored all of your data in a text file. Now you want to analyze and process that data. This type of processing is called offline processing because you have already finished acquiring all the data. A delimited text file is a common human-readable format. Many text editors, spreadsheet editors, and analysis tools can read and process a delimited text file, so you can use your preferred tool for viewing and analyzing the data in this type of file. For example, you could view, analyze, and process a delimited text file using Microsoft Excel. You can also use LabVIEW to easily read data contained in a delimited text file, and use built-in analysis functions and your own custom logic to process the data. To do this, use a Read Delimited Spreadsheet VI and an Array Subset function to extract the data from the second line to the last line as a 2D numeric array. You can then process the 2D numeric array. For example, you can transpose it, search its elements, run algorithms on its data, and more. There are three common file types that you might work with in LabVIEW: text files, TDMS files, and binary files. Text files are the easiest format to use and share, as many applications such as Notepad and Microsoft Excel can read from or write to a text file. Data is represented as strings in text files. TDMS is a binary file format created by National Instruments that is optimized for saving measurement data to file. You can use TDMS files to organize data and store information about your data. You can also use TDMS files to write and read data at high speeds. You can also use an add-in to view TDMS files in Microsoft Excel. Binary is a file format that you can use when you want to write or read from a binary file with a specific binary format. Here's a table comparing the three file formats. To continue learning about more I/O, go to the Advanced File I/O Technique lesson.